Hi, welcome to another video on my Raspberry Pi with pulse width modulation. Last episode and before that I have tried to get pulse width modulation working in such a way that I can drive a pulse width modulation motor and some LEDs over a few resistors. So far it kind of works, but I don't get the finger quite behind the relation between resistors and the pulse width modulation and voltage. I thought I had, but the results of last time with even 4 resistors, 1 LED and the pulse width modulation, turns out that according to my multimeter the resistance varies with the pulse width. So I thought it would be time to get back to some simulation using Scilab Xcos. So what I have done is an oscilloscope, a voltage meter, of course, connected to the ground, a resistor, and this resistor I have given a value of 343 ohms. That means that in practice for my circuit these are, let's say, 2 resistors. Then a voltage source AC. Now the point is that in my own circuit I use DC. However, with a pulse width modulation or pulse generator, in which I can indeed say what percent of the period the pulse width is, it has an input that can, as far as I can find, only connect to an AC voltage. And looking here, I can only set the frequency and not the voltage. So it will not be exactly the same. And then of course I have to connect this part as well, which is coming from or going to the ground. Having said this, there is some simulation possible, of course. So I am going to do that, and then you see something like this. So and you see the timing going rapidly. So much for simulation. So I want to try to change this, and let's say a phase delay in seconds, a period in seconds, amplitude. Let's vary this to, let's say, 60, and then you get this 55 not acceptable, 50 is not acceptable, and I say 49, which is acceptable. So let's run it again. And you get once again something like this. So I need to find out how I can get an acceptable pulse width on here on the scope. So let's find out further. In theory, if you have a 1 volt voltage and a 10% duty cycle, as you can set in here, then you have a voltage of 0.1. Now I noticed, of course, that if I do this, it says this can't be. So let me vary. If I say 0.9, does it accept 90? No. Let's go check further. It still doesn't accept it. What if I do this and so these are quite, in my idea, odd things. If I change this to an amplitude of 9, what does it do? It does. Periods in seconds, that is fine. Let me say 10 seconds. What happens then? Let's go. Okay. And then there's a 0 voltage right here. It says just 0 voltage. There's no pulse width at all. So the question is, why does it do that? Phase delay in seconds. What about 1.5? Right. Simulation in progress, but I don't see a simulation going on. It's a very short simulation then. 0.1. Alright. Simulation. There we go, but still nothing. I am doing apparently something not quite right. Question, what? Change this to 1. Still nothing. I suspect that this combination isn't as good as I thought it was. Well, I want it to be DC, not AC, and this is clearly AC. As the block name already says, fault source AC. So I need to find further how I can optimize this circuit to my own wishes. Okay, so I experimented a little bit and changed the frequency of the AC to 1 Hertz. Then before adjusting this again, I run a simulation, and this is the result. So now I have a visible graph, let me say it that way. Now let's see what happens if I change this. And now I get 50, but that is hardly other than say 95, 49, so let's change to 90. But that isn't allowed apparently. This is 80. So let's see what happens now. This is quite different. Very different. But again, this isn't. I wonder, this can't be pulse width, because everything has the same width. So let's try to change more, because this is. Let's change to 20. See what that is. That should be totally different. It is different, but not as I expected. Alright, let's change again to, but let's keep it to 20, but a period of 10. Huh. Now this is something completely different. Another change. This is an amplitude of 9, of course, and let's change to an amplitude of 5. That should be a complete difference. Yeah, right. So I want to and it is clearly an AC and not DC, but it's coming some way. So let's change something again. Phase delay 0.5 maybe. Not very remarkable. Yeah, this is wider. So let's change that a little bit more to 1.5. Not much simulation in that. Then 1.0. Not much simulation. Okay, let's go back to 0.5. Amplitude 5, make amplitude 7 for whatever. 20. Go. No. Apparently some settings just cannot be done. And there I am again. So this is an idea about how it can look. Still not happy with the AC, but it looks something like this. Yeah. So let's see further. So this is what the results are with 343 ohms. Now in the real circuit I have now 4 resistors, so let me change this value to 686. and see what happens then. It goes beyond 5. So how is the setting here? 7. Okay, so that is logical that it goes beyond 5. But I don't see a change here. Or do I? Let me go back to 343. Run again. And I see here, how much would I say? 2 centimeters? Yes, approximately. .686. Does it matter anyhow? That's what I wonder as well. So, yeah, back to 686. Run. Same. So does that make a difference at all? Putting a resistor in between. That's a very good question. And right now I am unable to answer that. What can I change more? Phase delay, let me put it down to 0.1, and let me put this to 80. That is apparently acceptable. Let's simulate. And then we get a very short bar. Very nice indeed. It would be nice if I could change this. Let's make this 5. If I could change this on the fly, but I have to try that. I never did that. So pulse width is nicely viewed, obviously. Let's go back to 20, because 20 is a white pulse. Yes. So the question still is, what does the influence of the, or how much influence does the resistor or resistors have? I'm absolutely not sure. And in order to check that, I could remove it. And then again, this is a simulation. And I have already often noticed that the simulation doesn't really represent everything in reality. So that's a big question. So for the last part of this simulation, I will remove this resistor and just go for it and see what happens. Yeah, there's no change. No change at all. So this proves that this simulation is not representable for the actual circuit. which actually also indicates that I should adapt the circuit to the real situation, and that is going to be a nice idea. Let me change, let me stop this, put the resistor back. Can I do that with undo, another undo? Yes, I've got it back. And again the values of the 686 ohms, so that is good. So it's kind of the same. The LED I have not put in there, but you can see the results here anyway. So I expect a simulation to run, but apparently and this is an ouch. Why? Failed. I don't like a failure. What's wrong with it? Let me save this first. Alright. So this is a bummer. Somehow it doesn't accept it. Change something to 30 or something. Let me try. Generate makefile. No. Okay, this is odd. But quite in line with my experiments, that some things don't go the way you expect them to go. Anyway, I'll reload this. Yes, and then I say I want to start Xcos again. What am I doing? I am loading something, but okay, I have to restart it apparently. Too bad. I can't even close it. Alright. So back to the real circuit, which is this part, and yeah, well, time to do some measurements to see if things are the way as I had set them up. So first of all, starting the program, PWM value at, let's say, 512, and last time the point was that 512 was pivot value, changing before and changing after, so I'm going to do different. I say 650 right now. So measuring the voltage, which is 2 volts, and let me measure right here on the pin of the, yep, it's 2 volts. So I put that a little bit wrong in the simulation, but apart from that, then here it is pretty much down to 1/2 volt. And of course that is due to the LED. So the LED does have absolute influence in everything. And now changing to the frequency, setting it to 20 kilohertz again, and see what happens. Everything should be the same. See, beyond scale, and here beyond scale. So if I change the value to, let's say, 126, beyond scale, and remember that the required pulse width for this motor is 40 Hz to 120, and that is way below the, let me show you, this is the setting for 20 Hz, this is for 200, for 20 kilohertz, and this for 200 kilohertz, and the fact that in this circuit it's beyond the scale of the 20 kilohertz, it will never work with this motor right now. So that's a very good question, how to realize that. Let me change now the value to 800. Beyond scale, let me change it, well, that shouldn't change when I measure the voltage, setting the limit to 20 volts. Yeah, it's about 3 volts. About 3 volts. But anyway, simulation isn't quite a match because of the volt settings, also because of the LED presence in the real circuit. But it's an interesting idea to simulate again. Let's see how that ends up. For now, thank you for watching, and if you like my videos, please subscribe to my channel. See also Instagram, Twitter, and if you like my videos, please consider to allow advertisement between the video segments, or see my website. URL can be found under my video. to see another way of donation. To be continued.